In this video, we will go over each graph produced by the basic analysis code explained in the previous video and describe how a solar flare might impact these graphs. Our first plot relates the radiation rate measured in counts per minute to the latitude measurements. The measurement taken over the minute-long interval smooths out any radiation fluctuations. Owing to this, it is a useful measurement for assessing the overall average level of exposure. While we only plotted the radiation rate per minute, the detector also measures the radiation over a 5-second period. The shorter interval presents a more precise and higher resolution plot of the radiation levels. Because of this, you may find it helpful to graph radiation measured in counts per 5 seconds to identify any sudden radiation changes or spikes. Here, we have an example of the minute interval latitude plots for two different flights. The first flight, from Cape Town to Amsterdam, crosses the equator during its journey, while the second flight from Paris to Tokyo does not. This difference has an impact on the shape of the plot. The Earth's magnetic field looks something like this. It acts as a shield from cosmic radiation. This shield is strongest at the magnetic equator, where the Earth's magnetic field lines are nearly horizontal in relation to the Earth. In contrast, the magnetic field lines are almost vertical at the magnetic poles. This means that the magnetic field is unable to deflect as many cosmic rays around the poles. As a result of this, a flight will experience more radiation closer to the poles and less around the equator. Going back to our graphs, we can see this effect. The first plot, which crosses the equator, exhibits a decrease in radiation around 0 degrees latitude. Comparing this to the second graph, which does not cross the equator, there is no apparent dip in the radiation levels. Rather, the average level remains fairly constant. The vertical increase and decrease in radiation seen in both flights indicates the steep rise and fall in radiation that the plane experiences as it takes off and lands. In both graphs, there is a slight increase in radiation levels before the plane lands. This is owing to aircrafts generally being lighter at the end of their journey as they have used up most of their fuel. This often leads to an increase in altitude towards the end of the flight. We will explain why altitude impacts radiation dosage a little later. Our next plot is fairly similar, but rather than latitude, it relates longitude to the radiation rate in counts per minute. Generally, radiation levels do not change as a function of longitude. However, our radiation data is measured as a function of latitude, longitude, and altitude. Since latitude and altitude are not kept constant as longitude changes, we expect to see a similar trend in this graph as we did with the latitude plot. That is, the radiation dose should decrease for flights that cross the equator and remain fairly constant for those that do not. Our third plot compares the altitude of the plane to the radiation rate, measured in counts per minute. As the altitude increases, the radiation rate should also rise. This is because at higher altitudes, there are fewer atmospheric particles between the airplane and cosmic radiation, and thus less shielding. Our next graph depicts the flight path, color mapped according to radiation levels. The color map scale runs from yellow to black, where the black areas indicate the regions with the highest radiation rates. As seen in the previous graphs, when the plane crosses the equator, the level of radiation drops. In this graph, the path fades from dark pink to orange. Solar flares are events in which the solar activity on the sun spikes. This increases the number of cosmic rays reaching Earth and has a direct impact on the radiation dose that a flight would be exposed to. Solar flares can also interrupt our radio and magnetic systems. For these reasons, measuring and learning more about them is valuable. The scarcity of solar flares means that fairly few measurements of them have been taken. As the sun heads into a more active cycle, we are hoping to detect more of these events with your help. We do not have our own solar flare data yet, but in the event of one, we would expect the graphs to change slightly. The latitude and longitude graphs may look something like this. The first change that you might notice is that the radiation rate skyrockets at the specific latitude or longitude that the plane crosses at the time of the flare. The average radiation rate in a typical flight, with no solar flare, is generally under 1,000 counts per minute, depending on the flight path and altitude. Solar flares will increase this radiation rate, so look out for rates higher than this, as they might indicate a solar event. After the actual flare, there is still more radiation in the environment than there was before. This means that while the radiation rate may decrease slightly, it will still level out at a much higher rate than the pre-flare levels. The altitude plot might look similar to this. Prior to the solar flare, the graph steadily increases as altitude rises. At the altitude where the solar event occurs, there is a sharp increase in radiation rate. Once again, after the flare, the rate remains higher than before, but will still decrease fairly linearly as the plane lands and the altitude drops. Finally, another sign that might point to the measurement of a solar flare is an unexpected dark black patch on the world map plot. We would expect the time before the flare to be mostly orange and the time afterwards to be a dark purple. Once more, this is because the radiation levels in the environment will remain higher for a while after the event. Thanks for watching. If you have any more questions, let us know. Good luck with the solar flare hunting.